basic techniques like decision trees and support vector machines work in the context of classification. So we will look at one category of algorithms which are useful in the context of machine learning, namely ensemble algorithms. The idea of ensemble algorithms, also known as meta algorithms, is that in meta algorithms you actually do not perform a single loop of running the machine learning algorithm. Instead, you form some kind of a control loop on top of a basic machine learning algorithm. So in that sense, it's a meta algorithm. It like has a control logic on top of a basic machine learning algorithm. So what ensemble algorithms are doing is, they're not algorithms per se, but they are some kind of a control loop on top of basic machine learning algorithms. Let us take the different types of ensembling that is possible. There are basically three kinds of ensemble algorithm techniques that are possible in machine learning. The first one is called bagging. Next one is called stacking. The next one is called boosting. If you see, bagging is, you can say, one of the more popular version and a simplistic version. Bagging refers to basically looking at the original problem space of input, then breaking the whole space into much smaller subproblems, and then producing a classifier for each small subspace, and then doing some kind of a averaging or majority voting to determine the final classifier. So what you do is, you take the original raw input, you convert them into many smaller classification problems, then you take the combination of all of them and take a majority vote or kind of an average and determine the final classifier. So here, if you can say that your classifier is something like a majority vote among, say, some hundreds of classifiers which are smaller versions of the original problem. Each one of these subproblems can be drawn from the original data with or without replacement, a small set of columns, set of terms, set of rows. Then we solve each of them, find separate models for each, and then try to do a majority of the vote for any new input that comes in. So what we've done is, in bagging, we have taken the negative effect of one large classifier for the original input data, having probably bias to the original input choice or very much varying with respect to different input choices. We try to remove those constraints or deficiencies by creating many small problems, solving them, and taking something like a majority. So this kind of a meta loop or an ensemble helps us in producing a more robust and more accurate model. In contrast to bagging, which is working on the idea of taking smaller problems and averaging them, in boosting, we take a different approach. We take an idea that a final classifier is made up of a weighted combination of several weak classifiers. By that I mean, if we have the original input, we created first classifier, this probably classifies 80% of data correctly, 20% doesn't. Then what we do is, we take the ones which it does not classify correctly, try to produce a second classifier which addresses the imperfections in this which are not correctly classified and does a better job at classifying those. Then same way we iterate over a certain number of times, and then we take a weighted sum of all the suppose some 10 such classifiers. So what happens is you get an iteratively improved classifier which works on the deficiencies of the previous version, but at the same time, unlike bagging, here we work on the entire original data set. So each of these is a weak classifier, and by combining each of the weak classifier into a final classifier, we get a much stronger classifier which is able to produce more accurate results for a major section of the input. So here we are talking about creating a strong classifier by combining several weak classifiers, but each one working on the entire input rather than on smaller input. In terms of stacking, it's a very simple meta loop where we run one classifier on the data, then we create a meta classification problem on top of it by saying that those data points have been correctly classified as true, those which have not been correctly classified as false, and this becomes like a data set now for another classifier. So what happens is we now take this as the input data along with the original input data, we add this as another field, for example, and we try to compute another classifier on top of it. Say for example, first one we did random forest, or we did say logistic regression. The second one we can do addition. So for example, if we did random for logistic regression here, we try to find out which rows have been classified as true, which have been false, and then we try to run a classifier on top of this additional augmented data where original data is added with this additional column of true, false, which is basically the result of the classification of the previous one. So in that sense, what we're doing is we're trying to stack one classifier on top of the other. You can create multiple stackings of classifiers, one on top of the other. Basic idea is you're using the result of one classifier and using that as an input for another classifier. In fact, stacking is shown to be a very effective data science technique or machine learning technique for several competitive kind of machine learning competitions. So you see, in all of this, the meta algorithms, we're not running one core algorithm like addition tree or linear regression or logistic regression, but instead we're doing some kind of a control loop on top of a basic version of an algorithm on the original data. Each one has its own spirit. Varying has averaging effect. Boosting has continuous improvement. Stacking is like using the result of one to as input for the next level classifier. All of them are separate. Each of them has a different spirit. And meta algorithms are proven to be generally better in terms of accuracy and performance and evaluation measures than single pass measures.